Thanks everyone for coming to the QFT in Physical Mathematics seminar. Today we're happy to have Liyuan Chen from the physics department. He's going to tell us about constructing a large-scale quantum computer based on a TQFT.
Hello everyone. I'm Liyuan, and I think today is a very abnormal or very special topic. We try to combine QFT and quantum computing, and thank you for coming to this talk. So this is based on the joint work with these co-authors. I am Liyuan, and Yuan Jie is a PhD student at MIT, working with Peter Shaw. And Ruihua, right now, he is a postdoc fellow at Berkeley, and Arthur is my advisor here. Yeah. So I will just give a very brief introduction about how to think about the basic idea why we need to use TQFT to construct this quantum computer. And before that, I will introduce what's the basic requirement of constructing a large-scale quantum computer. So to construct a quantum computer, I will use just QC to represent it. You actually need several things. You need input, and you need some unitary to do computation, and you use measurement to give you the output. So this is a typical process of doing computation in a quantum computer. But we need to realize all of them reliably, like the input is some set of maybe qubits or some other different ways to encode information. And we can have a unitary gates to perform this computation. And finally, do some measurement to read out all of the things. During this process, there are actually two very important concepts to actually realize a large-scale quantum computer. The first one is called universal quantum computation, or I just write it as UQC. And another one is called quantum error correction, or I will call it as QEC. I will explain these two concepts one by one. So the first one, universal quantum computation. This means that this unitary needs to be general enough. As an example, our input is 0. And then I apply just Pauli x. X just go from 0 to 1, 1 to 0. This will give us 1. This is nothing, just a NOT gate in our classical computation. So if we only have such a simple unitary, it does not give us any quantum advantage. To have a quantum advantage, we must realize a universal quantum computation like any large unitary we want in this circuit. So to realize this universal quantum computation, there is a concept called universal gate set. This is a set of 1 qubit or 2 qubit basic gates. By combining together, we can simulate any large unitary we want. Like one example will be Padma as C0 plus T. Yeah, let me just give a very brief introduction. What are they? These are just called Clifford gates. And this is another magic gate. If we think about qubit, 0 space as a vector, 2-dimensional vector, this T gate will be just a 2x2 matrix. It's a pi over 4 rotation on this one state. And actually, other gates similar. And typically, there is a theorem called Gauss-Mannil theorem that these Clifford gates is classically simulable. So that's why I write it as magic, because actually this T gate is very special. It actually gives us the extra computational power compared to classical computation. Okay, so this is a very short introduction. And yeah, let's keep in mind this T is important. I will explain why it is important in this part. So if we want to just simply realize a universal quantum computation, it's very, very simple. You can have one atom. You have atom, and then you just tune its states, and you can do any computation you want. But this is not good enough. because any small perturbation like noise or thermal fluctuation will break your information encoded in this atom. So that's why we need to do quantum error correction. Actually, nowadays, the error rate in the quantum circuit is very large. So there may be many errors at some cross happening everywhere in this quantum circuit. So we need to do error correction to remove all of this error to have a reliable computation. And the basic logic is like we encode many physical qubits into one large logical qubit, such that we can compare the parity between neighboring qubits. If this one is flipped to 1, or we can see there is some mismatch between the neighboring qubits, and then we can correct that by just doing some reverse process. So to actually do this thing, people have constructed many error correcting code. So I write it here. This is the name called error correcting code. To do this encoding for multiple qubits into one logical qubit. And the most famous one and the first one is proposed by Shaw. He is at MIT now in 1997. And maybe one of the most widely used one is by Kitai, proposed in 2003. This is called surface code. This is like we have a two-dimensional surface, and we put this qubit on this two-dimensional square lattice. On each edge, we have a qubit, 0 or 1. And then we always measure the neighboring qubits by this operator. This is a function of Pauli X operator, and this is a function of Pauli Z operator. We measure this operator for each site. You see, this is a site and the several edges out of this site. And also this is a plaquette. We measure this operator for each site and each plaquette and detect like a neighboring qubits parity. And finally, we can detect the error and correct that. We will not go into the details of this part, but this is a typical way to do this error correction. But why I need to mention this surface code? Because I mentioned this T here. So you may imagine that we have some way to do error correction. In doing this error correction, if each site we have some probability P to have an error, there is a concept called error threshold. When P is below this error threshold, the logical error rate, there is also a proof by Kitai in one of his follow-up paper. The logical error rate in this encoding will decay as exponentially in terms of system size. Here, this alpha P is a function greater than 0, and this L is the system size. This means by increasing the system size, we can like exponentially suppress the logical error rate by doing this encoding. So quantum error correction is very important to suppress the error in this quantum circuit. So you may imagine that we have a universal computation, and if we can replace each physical qubit by this logical qubit doing error correction and apply this universal computation on this encoded qubit, we are done. We actually combine this UQC and this QEC successfully. So we can realize fault-tolerant quantum computation. But it is not easy. Why? I actually mentioned this T here. A conclusion is that even though you can realize these gates logically in this code, there is no T with their fault-tolerant version. So the conclusion is that in this surface code, you cannot realize a fault-tolerant universal gate set. Yeah, this is the answer. So if we want to realize universal quantum computation using this encoding, we need some other method. The method is very simple. This is called magic state distillation. Because this T is called magic gate, so this is called distilling this gate. Like you have some protocol, like you have multiple T's, and you use the distillation to distill it into one T with higher fidelity, and then do that again and again and again. So you can see the initial copies of T actually grows exponentially. So this is very expensive. Doing this distillation is very, very expensive. And typically to realize a universal algorithm, over 90% of the results on the qubits are from this part. This is called a magic state distillation. Magic state distillation. And this was proposed by Ravi and Kitai 2004. So the motivation is here. We want to do UQC plus QEC, but we don't want this magic state distillation. And how to do that? And that's why we want to think about topological quantum computation, which is inspired by this principle of TQFT. So let me give a very, very brief introduction about this part. So I will erase this, but I will keep this QEC part. Topological quantum computation. This is actually based on the principle of TQFT. So I will give a very, very brief introduction. As we learn from like basic quantum mechanics or quantum field theory class, we know like there are some anyon statistics or just particle statistics in 2D. Like for two particles, I call them alpha 1, alpha 2. They are identical particles. Then we exchange their position. We will get some space in front of them. If it is boson, this is +1. If it is fermion, this is -1. But we can have other possibilities, like we can have other than this +1 and -1. And these are called anyons. Yeah, people have encountered that maybe in some TQFT literature. Then this TQFT actually are completely determined because the Lagrangian of TQFT is 0. So the TQFT are completely determined by the anyon data. These data are called N, R, and F. Yeah. What are they? I will just explain two of them. What is N, what is R, and F, I just leave it here. So N is corresponding to this fusion or splitting. Like we have alpha and beta anyons, and we fuse them into gamma anyon. This is governed by this number. This is called like something like a multiplicity, like whether this process is available. If they are available, it's greater or equal to 1, but they are integers. Otherwise, they are just 0. So this is a process called alpha and beta fused into gamma. And braiding, the other one is called braiding. Braiding is nothing but just this process. We have a pair of anyons, beta and alpha, maybe originated from some gamma. Then we do this braiding. What's the result? The result is R, a phase called R symbol of this original configuration. And F is another symbol that's more complicated, but I will just leave out here. So this N and this R and also this F determine the dynamics of different anyons. And we can think about this as just anyon word lines, like this is a time. And they are in this two-dimensional space. So we have this kind of three-dimensional space-time trajectory. Then why people believe topological quantum computation is good? This is because there are two things. The first one is this is very complicated. They are actually the representation of the braid group. So they are very, very complicated. And you can see here you have many choices of phases. And another thing is this N alpha beta gamma. If alpha and beta, they are both non-Abelian anyons. the fusion result can be like many different other anyons. So this is a defining property of non-Abelian anyons. We have multiple fusion results. So people believe that the multiple fusion results and the very complicated braiding phases can give us extra computation power. And that's why people believe topological quantum computation, or in short, TQC, can realize universal quantum computation. But there is a tricky point. Even though we can realize universal quantum computation, I still did not talk about this quantum error correction, QEC. So how can we believe that it can finally be a good candidate for universal fault-tolerant quantum computation? And this is the point. Yeah. Why it is called topological? The topology is actually hidden in the anyon types. The theory is like, if a pair of anyons, anyons are always created and annihilated in pairs. And if a pair of anyons are far away from each other, like these are the spatial distance, they are far away from each other. Then if there is a small pair of local anyons created by some thermal noise or some other process, they have some probability P. When we detect that, we can compare with our original configuration. This is our desired configuration, and we can see this pair is unwanted. So we can always fuse them by pairing them up. This is very similar to the process, like we have many zeros encoded into one logical zero. And there is one zero flipped into one, we can detect that and correct that into the original one. So these far separated anyons are just this repetition of zeros. They are actually very equivalent. So this is called topology. Because in the theory, if you just check any models in the topological quantum computation or TQFT, people will say that, okay, these information are global and then local perturbation will not affect this global information. This is very similar, like some small deformation, not like a puncture in this manifold. Yeah. So if we can use anyon type to do encoding, I say encoding. This is very similar to build an error correcting code, and we can correct local errors. And because they have the possibility to do universal quantum computation, it seems we have good way to build a quantum computer. But again, there are many tricky points. Our goal is to use topological quantum computation to do these two things. But there is a tricky point, it's called experimental feasibility. Yeah. Over the last 2 decades, people have tried to find these non-Abelian anyons in experiments, like Majorana. And also recently, Microsoft said that they found Majorana in experiments, but this is still like under like debating. So yeah, so people try to find this, but it's very hard. So like how to have a good way to find this non-Abelian anion, this is the first problem. And then how to find a good way to do this computation in a fault-tolerant way universally is another problem. And actually, during the past decade, 1 decade, people have found that the quantum double model S3, DS3, may be the sweet spot to combining all these 3 possibilities. I will explain this later. But firstly, I will just give you some review why it is believed to be the sweet spot. The first one, for this UQC part, there was an old literature by Cui. He is now a professor at Purdue University in mathematics department. They have shown that you can use anyon encoding, and you can do some operation to do universal quantum computation. And then for this quantum error correction part, there are some papers. One is by Wutong and their collaborators. One is by Scotty. Show that non-Abelian anyons can have error threshold. So quantum error correction is possible in non-Abelian anyon model. And lastly, and recently, for experiments, there are some papers, for example, by Rosen. He was a postdoc at Harvard, but right now he is an assistant professor at Chicago. And also by Brawley, a very famous guy in quantum information. They have shown that you can use quantum circuits to prepare quantum number S3. So quantum circuit is something that is very hot. Recently, everyone talk about qubit and qtrit. You use qubit and qtrit together you can construct this quantum number model S3. So it seems that we have all the things we want, but the problem is that, as I mentioned before, you will face a compatibility problem. On one side is good, does not mean that on all three sides is good. And in our work, we want to solve this compatibility problem. Namely, we want to combine all of these three things together to give a comprehensive blueprint to build a large-scale quantum computation, a large-scale quantum computer based on this quantum number model S3. And this is our contribution in this work. Yeah. So let me give a brief introduction. What is quantum number model S3? Yeah, we have talked about that for a long time. It has many good properties, but we don't know what it is. It is actually a lattice model. Like, very similar to the surface code, if you still remember, in this two-dimensional plane. It is also in this two-dimensional plane. It is a lattice model on square lattice. Let me draw this like this way. Yeah. And then on each edge, instead of a qubit, we have a group ring of the Hilbert space, where this G is in group S3. S3 is a 3-element combination group, has already 6. This is the smallest non-Abelian group. And then for this model, we have 8 types of anyons from A, B to H. These two are called Abelian anyon. Namely, their fusion will only give us one result, and the other are non-Abelian anyons. Okay, in this two-dimensional model, what are the important facts? This was shown by Kitai and also proposed by Kitai. That the operators, the operators to control the anyons in this two-dimensional model has one-to-one correspondence with anyon worldwise in the category theory. Let me give you an example to explain what's meaning of this. For example, if we want to create a pair of C anyon, this is realized by an operator called F rho C. Rho is just the support of this operator. It's like a two qubit operator, something like that. And then this C is just creating a pair of C anyons. This is equivalent to creating a pair of C anyon from vacuum. Yeah, this A anyon is the trivial anyon, is the vacuum. And we create a pair of C anyon from vacuum. Then, if somewhere else I use another ribbon operator called F rho D, create a pair of D anyons. This is equivalent to nothing but just doing this. Then, if we want to manipulate those anyons using some other operators, yeah, for example, like just exchange the position here, exchange the position here, you will see this is a process of grading. creating this C and D anion. And finally, if I perform some measurement here using the operator called KS, this is another operator in the model. You will get this fusion result of these anions. So in short, this is a lattice model with some operator F and K on it to manipulate those anions, to create anion pairs, and to break those anions, and finally can fuse anions to measure those anions. This has one correspondence with this one. They can reproduce this TQFT on lattice. And why we want to think about this model? Because when we have this lattice model, we actually have a way to build that in quantum circuit. And this is the basic idea of these two groups of people. But in their paper, their construction, first one is not fault-tolerant. And the second one, they are not compatible with anion fusion. And in our work, this is our first contribution. Maybe I write it here. This is our first contribution. We constructed circuits for this F3 anions, and they are compatible with fusion, such that we can use anion fusion for the local pair to do quantum pair correction. And this is very detailed, so I will not go through the circuit construction here, but I will just give a very brief sense why it can be done in this part. This is because on each edge, we actually have a group element. And in S3, there is an isomorphism. S3 is a semi-direct product between Z2 and Z3 group. So that's the reason. Z3 you can think about as a qubit. Three-state system like K, where K is 0, 1, and 2. And also this Z2 is nothing but just a qubit. So it is like qubit L is 0 and 1. And that's the reason. You can encode that into qubit and qubit. And these are very available in current quantum platform like Rydberg atoms or ion traps or superconducting qubits. So you can think about how to realize them in the experiment. By encoding that, and you write down all of these operators in the circuit form. This is non-trivial, but very, very tedious. But write them down, you can have this construction for this one, for this TQFT on quantum circuits. So this is the logic. Then we will go to the key part. We have one way to realize this to realize this S3 on the experiment. But how can we do other two things like universal computation and do quantum error correction in this process? Yeah. So I will erase, maybe just erase this part here. I want to keep this part. Okay. So the first step, now we have some sense to do this, and we want to go to this part. I will introduce what we did in this universal computation in this quantum level S3. The key is that we want to realize that in a fault-tolerant manner, in a potentially fault-tolerant manner. And then, as we have mentioned before, the fault tolerance is from the anyons topology. When anyons are far away from each other, local errors can be detected and corrected. So if you can keep the anion far away from each other, and all of your operations during the process don't move the anion close to each other, we can somehow ensure the information are not corrupted by local errors. And this is actually a protocol using this anion type as encoding, just by all. Their encoding is by this way. This is a fusion tree for D anion. I remember there are 8 types of anion A to H in this model, and they use 4 D anion to fuse into 1 G anion to do encoding. Intermediately, there are two unknown anion. These are unknown, and I use that to encode a logical qubit. Yeah, I know this is a little bit abstract, so I will explain that very clearly what happened here. This is a fusion tree. Remember, every anion moduli has its correspondence in this two-dimensional lattice. So if we think about in a two-dimensional lattice, this is like we create a pair of D anion here, another pair of D anion, D anion, D anion. We create 4 pairs of D anion at some place, and then we move this one of these D anion together to one side, and then we fuse them into G. So this is actually the physical process to prepare this state in a two-dimensional plane. Then this D anion is moved to this side, so it's not here. Yeah, and in this case, we don't know the intermediate fusion result X and Y. So they can encode logical information. Because if we can always see this information, there is no quantum coherence. And the coherence is hidden here. So yeah, this is the way to do logical encoding. And during the process, we can only see those D anions and G anions. And the internal information are unknown. And that's the way we do some operations on this thing, we can do some computation. Why it is called this is called a U model. I didn't write it here. This is called a U model. And why it has this name? Because the author only used a subspace of the possible fusion result here. XY is in a subspace spanned by some intermediate anion type called AG, GA, and GG. They are just certain types of anions. This is U. Why I need to write it here? Because in their paper, they have proved that. They prove that braiding is D anions. Yeah, these D anions plus 2 measurements called MA. MA stands for the measurement, and U plus some operation called multi-qubit CZ can realize a universal gate set, universal computation. And yeah, that's the key point, and this is our key contribution in this process. Even though they show this thing, it is not sure why or whether they are fault-tolerant. Braiding is very easy to see it is possible to be fault-tolerant. Because if we can keep this anion far away from each other, braiding is just exchanging their positions. During this process, if their distance is very far, it is very large. The local errors maybe here will not interfere with information encoded in this time. So this is good. But measurement is problematic. These 2 measurements, yeah, let me just introduce them. This MA, you want to distinguish whether it is AG or whether the space is spanned by GA or GG. Namely, when we are in this subspace, we want to distinguish these 2 subspaces. This means we want to measure the first 2 anions, whether it is A or G. And you will immediately see this is problematic. Why? Because typically we do measurement by doing fusion. We move 2 anions together. And we measure their total charge. But typically we will think, we move these 2 D anions together and to see whether they have total charge A or G. But this will immediately reduce the distance from D to 0. So this process, yeah, let me write it here. This will reduce the distance from D to 0. And this will immediately ruin any fault-tolerance encoded by this large separation between anions. The answer is there is no fault-tolerance. If we naively do this fusion and measurement. And this is the same for this MU, but I will not introduce what is MU here. Actually, it's a projector into this U subspace. And this one, in their paper, they say that this is very, very strange, but this is necessary. They don't know how to realize that, and they don't know how to realize the fault-tolerancy. Actually, these two measurements are not how to realize the fault-tolerancy and also this operation. So right now, this is our contribution. Yeah. What we did is, yeah, this is our contribution, and I first write it here. This is our second contribution. We realize all operations in this U model remotely. Namely, we have some way to do this measurement without fusing the anyon together. And this is realized by process we created called anyon interferometry. Yeah, so interferometry is something that we learned from our high school physics. Like we use some particles, go around some other particle and see the interference pattern to determine the internal particle. This is the step. Like we want to, for example, if we want to distinguish whether the first 2D anyon has total charge A or not, we use some well-separated anyon far away from it to do some interference with it and to measure that. This is like, we have this fusion tree, D, Okay, now at very far away from here, we create a pair of D anyons. And then we braid this D anyon with these two D anyons and come back. During this process, their distances are always very far, very large, D. And then when we come back, we fuse with the original D anyon and we see this W anyon. And then if we want to come back to the original space, we just fuse this W with D. What is the conclusion here? By some very tedious calculation using category theory, you can show that when W is A, this X is A. When W is G, this X is G. So we realize this measurement M8 by doing this interferometry without touching this anyon, without moving them together. So this is a key process. You want to realize the fault-tolerant universal computation in this U model. And also for this MU, we also realize that. I just briefly summarize it here. For this MU, you also create a pair of H anyon and do this braiding, come back, get a W, and fuse that with this anyon. Also by some calculation, we can show this is also, like, you can realize this MU. Okay, in this process, we also check any local errors will not affect this X and Y internal states. So this is the way you always keep them far away. And then we realize this universal gate set in a possibly fault-tolerant manner. And this is our second conclusion. We realize all operations in this U model remotely. This actually solves an open problem, whether quantum double S3 can do universal fault-tolerant quantum computation. Our answer is that if they have a threshold, yes. This is very important. And then for this multi-qubit gate, I will not go into the details, but the summary is like the previous gates are just single qubit on a single tree, and this is for multi-trees. But this one can also be realized remotely by combining our braiding and our interferometry protocol. This is the answer. So all operations can be realized remotely. Yeah. So this is very exciting because this means that we can use that to build a quantum computer. So we actually go to this part. We actually, we can realize this part. And then you can use experiment to repeat this. But there is a tricky point because we still need to consider the quantum error correction. Right now, I say that you can do this encoding using this anyon type. But whether it is actually correctable, error is actually correctable, you need to know whether you can suppress the error rate below this error threshold. And this is the part. Yeah, let me give you a reminder what happened here. So a reminder is that by definition, error threshold is when you have P less than is PC. Your logical error rate will be suppressed to exponentially minus alpha P L, and L is your system size, so it is exponentially suppressed. But right now, we don't know whether it is PC exists for this quantum double S3, and this is what I'm working on. So I should say this part is not completely solved, but there are many evidences showing that there is a threshold for this quantum double S3. Like for Ising anyon, this is by Wu Tong. Now, the threshold is 10 to the minus 70. And for Fibonacci anyon, this is by Scotty. At 2022. This error threshold is around 10 to the minus 4. So what's the meaning of these values? Currently, for any quantum device, we can only suppress our P to around 10 to the minus 2 or 10 to the minus 3. So if you want to go to maybe some very small error threshold below this threshold, it's very difficult. So yes, so this actually is very challenging. And for quantum double S3, because there are some like common belief in this field, quantum double S3 is a system between this Ising and Fibonacci. Even though we have not explicitly worked out the threshold for this model, we believe there is a small but finite threshold, like very similar to this kind of order of magnitude. So we need to think about how to suppress the physical error below the below this very possible small error threshold.
What is the meaning of this threshold? Is this saying that if the underlying lattice system of components meet that threshold, then you'll get a topological theory?
Yeah. So this is the meaning is like we always have a two-dimensional system, right? And they have this system size maybe L by L. And then the threshold is for like if you assume single site or single edge error has probability P. And then when P is below this threshold, your logical error rate will be suppressed exponentially in terms of system size. This is like when your error rate is small, they do not accumulate. When your error rate is high, they accumulate when you increase system size, like some phase transition. Yeah. So the logic is like we will expect S3 has a very small threshold. And we have some way to suppress this below this threshold. This is the logic. And how to do that? This is our last contribution. Yeah. Yeah, let me write it here. This is our third contribution. We have a way to suppress circuit level noise. What do I mean? Previously, I have introduced. We can encode each physical distribution from a group element into a qubit and qubit pair, right? By just using this isomorphism between this S3 and Z2 and Z3 to encode that into qubit and qubit. And the further thing is that we can do that, encode that into a logical qubit and logical qubit of some local error correcting code. Local error correcting code. This is like, yeah, on the lattice. Originally, on each side, we put a qubit and qubit. Right now, we put the error correcting code here. Then, and this side, originally it has error rate P. Right now, it becomes the error rate of the logical error rate of this small error correcting code. This is a logic. But doing this, meaning that we have to pay something. What do I pay? what I pay is that this error correcting code needs to have all logical gates in the S3 circuit. Namely, if you want to apply unitary gates on this error correcting code, they should have these logical gates in the original circuit, in the physical circuit of the S3. Yeah, let me remind you, if you still remember, for surface code, why we cannot do fault-tolerant universal quantum computation? Because there is no logical T-gate. And this T-gate is called magic gate. It's very special. And actually, in the circuit of this quantum number S3, there is also another magic gate. This is called CMSA. This is a charge conjugation. What is operation? Let me firstly write it here and let me explain why it is necessary in this case. The CC hat applying on a qubit and qubit will give you the flipping of the qubit depending on the qubit. When the qubit is 1, we flip this qubit to its minus value, opposite value, sorry. When it is 0, we do nothing. Why we will have this magic gate? Because if you think about the generator of Z3 and Z2 as mu and sigma, the semi-direct product structure of S3 is from sigma mu sigma conjugating this Z3 generator by this Z2 generator, give you this mu inverse. So that's the reason. You see, if you want to capture this algebra in this circuit, you must have this gate to flip the qubit by this qubit. That's the reason. And this is a magic gate. This is a magic gate. This is a magic gate. And typically, it is very hard. This is a conclusion. It is very hard to have magic gates as a logical gate in those stabilizer error correcting code. But we are very lucky. We find one to have the code to have this gate and all other gates in this quantum number S3. So we have an effective way to suppress the error arbitrarily. Here I said, yeah, actually I didn't write this word arbitrarily because we can choose this is a family of code. You can choose any odd integer n. So you can choose a very large n to suppress this error very small. So we have the hope to let this p go below this PC. Yeah. So these are the contributions we have in this paper. In this paper, we actually answer this question, whether we can successfully find some way to realize topological quantum computation in our nowadays device. And the answer is yes. So yeah, so to give a summary, it's just this part. We have the circuit for manipulating those anyons, and then we can realize this universal quantum computation in a remote manner. This is very important to realize the fault-tolerant universal gate set. And then we can have the way to suppress the circuit level noise below this error threshold. Then what should we do next? As I have mentioned many times, during this process, our assumption is that we can always correct local errors. And this assumption is based on the assumption that there is an error threshold for quantum number S3. Even though there is a hint, like for Ising anyon, for Fibonacci anyon, we have this threshold. We have not shown whether quantum number S3 has this threshold. And this is what I'm working. I'm doing this. Yeah. If we can finally find this one, we can give a confirmative answer. This is one path compared to the current protocol. You can use that to build a quantum. So this is one future direction and I'm working. And the second one is, even though maybe you have this threshold, it's a way to do this. And you don't need to do magic state distillation. It seems that it is very good, but you still need to calculate the overhead of this model. Like, if you want to show that this is advantageous compared to maybe surface code or current other protocol, you need to explicitly calculate the resource you need to do this computation. And this is what I'm also doing. We try to think about whether it is good. And there are some other ways, like you can think about other topological orders. Other topological code value is good. And also, I may also think about whether this can be actually realized in experiments and whether we can develop some algorithms that is very efficient in this model that can have some nowadays application using this quantum computing. So these are some outlook, future direction based on this work. Yeah. So if we can finally realize all of these, like we believe that we actually have a new way to realize quantum computer compared to current protocol, and this is based on TQFT, a problem people have think about it for many, many years, 30 years, I think. Yes, thank you very much. This is what I prepared today.
So we'll talk, Liyuan. Do you have any questions in the room?
Please.
Yeah, thanks. It was very clear talk, very nice. You cited some experimental work, and there's early you mentioned the enhancing experimental work, producing anyons.
Who was
Various that was
Arizona? Verizon. How do I? Yeah, I don't. Oh, you mean Verizon? Yeah, yeah.
So what did they actually do, and how close was it to what you?
Yeah, yeah. In their paper, they actually collaborate with Continuum, right? They actually realized qubit Tori code. I remember. This is what they get. And firstly, this is different from S3, definitely. And secondly, but this is very helpful because we need to qubit. But the third thing is that at the point they posted their paper, we didn't post our paper, and their protocol is based on some protocol that is not fault-tolerant. I mean, here, this actually is the key point, and the encoding is very different. In their protocol, they use, I remember it's Muchong, and Muchong is a student of Kitai. And this protocol locally use freedom of S3 to do encoding. So this encoding is not fault-tolerant. I believe before we actually write this paper, there is no way to show this is fault-tolerant universal computation possibility for S3. But I am very glad that if I can collaborate with them to do this experiment, realizing this one. And
how is this realized? Is this some superconducting?
You mean this one? This on ion traps.
Ion trap. Okay.
Yeah. Continue. And I actually communicated with them because we have many communications with Ashwin group, and they say that why they cannot realize a full S3 is because the number of qubit and qubit is not largely enough. For S3, you need a very large number of qubit and qubit. Yeah, very good question. Actually, you mentioned this. I didn't mention this in the talk.
Anything else in the room? Any questions over Zoom?
Could you talk about how you're setting this threshold?
Yeah, I can give a very brief introduction how to calculate this threshold. Like, yeah, because we still have some time, I can just, yeah. So for this is actually very, very different from the threshold. Like in surface code, how do people calculate the threshold? It by just be sample errors, like sample the X here with some probability P, and we sample those errors, and then we do some decoding and do error correction, and to see whether they finally produce a logical error or not, and to give you plots. Like this is a plot, logical error versus physical error, and then if you can observe some threshold value here, and different lines corresponds to different L, different system size. Maybe this is 12, this is 10, this is 8, different size. You will have a crossing here. This is the error threshold. Namely, you can expect that for L goes to infinity, then the error rate is below this threshold. You can always suppress this logical error rate by decreasing system size. And then this is somehow very similar in our process. We also actually create the two-dimensional lattice of this quantum S3, and then we sample errors, everywhere, and then to do this, to develop some decoding algorithm, error correction algorithm, and to see whether we produce a logical error. But this is very different, is that the surface code, as I mentioned before, they are classically simulable. Because they do not have these T gates, they are actually classically simulable. So this is very efficient to do the simulation. But this is a universal model. You have universal computation power, so it is not classically simulable. So we actually need to find some way to do this simulation. And this is very tricky. If you are interested, we can talk about that later. But the answer is right now, we have finished the simulation in 1D. It is efficient. I sent it to Arthur. Arthur has seen this result. And right now we are approaching to this 2D, because 1D is like some practice for this anyons error correction. And right now we are going to simulate that in 2D. And when we get this result, we will write this paper and tell people, okay, we get this result. It is possible to do the computation using this model.
Even again.